This is Daniel Coosbury, and in these last three lectures, we're going to leave geometry and delve into a little bit of elementary statistics. We're going to start out in this one with a lot of terms and things that may or may not be new. Kind of an overview of statistics. When you do statistics, there's some sort of population that you're interested in learning about. So imagine just a bunch of things or people or some sort of population of things, and you want to know things about it, but you don't actually have all of the information available to you. So just imagine the population of the United States. We want to know things about them, but we can't exactly get information for every single person about anything we want. So what we do is we take a sample of that population, and so imagine just kind of reaching into this box. This box is the population. A sample is just something we take out of the population, and we use that sample to try to deduce some things about the population as a whole. So in practice, whatever I'm interested in learning about, we'll call it the population. The big thing, I don't have the data of all the population, but it's some big thing. I take a sample of it, and I use the sample to try to learn about the population of a whole. So a lot of this lecture is going to be kind of how to sample well or how to sample poorly. And we're going to look at a few samples of data and just some ways of representing that in this lecture. So here is an example. We have a group of hotel owners in a large city decide to conduct a survey among citizens of the city to discover their opinions about casino gambling. So question A says describe the population, and B says, well, let's do A first. So A says describe the population. We're interested in conducting a survey among citizens of the city to discover their opinions about casino gambling. So citizens of the city is going to be our population. All the citizens of the city is who they're interested in. So we'll call that the population. But they're going to make a survey of people from the city. So they're not going to ask everybody. They're going to take a sample from the city. But as far as the population goes, that's this big group we want to learn something about. So we'll call that the population. B says, one of the hotel owners suggests obtaining a sample by surveying all the people at 6 of the largest nightclubs in the city on a Saturday night. Each person will be asked to express his or her opinion on casino gambling. Does this seem like a good idea? So this question is kind of broad. Does it seem like a good idea, yes or no? You could argue yes or no, but what we're interested in is how the entire population of the city feels about casino gambling, and the proposal is, why don't we sample or survey people at 6 of the largest nightclubs in the city on Saturday night. Now, do you think if you went to those 6 largest nightclubs in this casino, are you going to find representatives of the entire city, or are you going to find a bunch of people who like to go to nightclubs and maybe gamble on a Saturday night? We're going to say that this is not a good idea because that this sample is limited to people who probably have some sort of bias towards casino gambling. So we're going to say this is not a good sampling method just for that reason. So if in practice, then if you really wanted to get an idea of the whole population, maybe go into the phone book and randomly pick out 1,000 names from the phone book. It would give you a much less biased perspective than going to a place where there may or may not be a lot of gambling and asking all those people, because they're probably leaning towards the gambling thing. And we want a really unbiased sample. So you're going to see some questions like this where you have to look at the method and decide if it's a really good idea or not. Try to poke holes in the method. The best kind of sampling that we like to do in statistics is called random sampling. It's different than going to a particular place and picking out a few people we really like those nightclubs. Random sampling is a sample that's obtained in such a way that every element in the population has an equal chance of being selected from the sample. So a random sample, a sample that's perfectly random, isn't going to be biased towards picking out a specific subgroup or particular people who might fall into one camp over another camp. Purely random sample, every single element in the population has an equal chance of being selected. So you take a sample, you may get 1,000 particular people. You take another sample, you may get 1,000 different people, and the chance that you pick any one is the same as the chance you pick another one. So let's look at this example. We have the city council of a large city needs to know whether its residents will support the building of 3 new schools. the council decides to conduct a survey of a sample of the city's residents. Which procedure would be most appropriate for obtaining the sample of the city's residents? So A says survey a random sample of teachers who live in the city. So there may or may not be something good with that. B says survey 100 individuals who are randomly selected from a list of all people living in the state in which the city in question is located. C says survey a random sample of persons within each neighbor of the city. And D says survey every 10th person who enters City Hall on a randomly selected day. So these might all sound like good samples, but we're going to try to pick the best way to sample. For one, we're interested in whether or not the residents of the city as a whole, so these are the residents, the city residents, the large city residents, whether or not the residents as a whole will support the building of 3 new schools. So A says let's survey a random sample, I like random samples, of teachers who live in the city. Now, if we're asking about teachers, only teachers, they may, kind of like that casino example, they may or may not be biased towards building a new school. A sample of teachers does not necessarily represent the entire population of residents. They only represent a little subgroup, and this particular subgroup has a little bit of bias when it comes to education. So this wouldn't be a perfectly random sample of the city residents, something that we're really interested in. So we're going to rule out A. Namely because they're teachers. We're really not asking a ton of people who fall into different categories. We're just asking one little group, and that's not going to be good enough. I'm going to rule out D also. Survey every 10th person who enters City Hall on a randomly selected day. This may seem okay, but at the end of the day, there's only a very, very, very small population of the city that's actually going to enter City Hall any particular day or even a particular week or month. So you may not even get a big sample this way, but also you may leave out a huge portion of people from your population who maybe don't live near City Hall or just aren't interested in the goings on of, I don't know, but this seems to be limiting things too, seeing as there are a couple better options here. So these two seem to be better. B says survey 100 individuals who are randomly selected, so this word random is good, from a list of people living in the state in which the city in question is located. This sounds fine, except that the city council is interested in knowing whether the city's residents will support the building of the 3 new schools. So we're only really interested in what the city residents think, whereas this has you asking people who live in the state, not necessarily in that particular city. So as far as the city council is concerned, they don't really care what the people in other cities in the state care. They're more concerned with their constituents, which is the people in their city. So we're going to rule out this and then talk about why C is the best answer. He says survey a random sample of persons within each neighborhood of the city. So if you want to imagine, this is my population box again. Imagine that all of these are my neighborhoods in the city. And what this is suggesting is I go in to each one of these neighborhoods, which are going to be all over the city, and I'm going to sample just a few people randomly from each one. So everybody in each neighborhood has the chance of getting selected equal to some other person in that same neighborhood. And if I do it this way, and maybe I only sample 100 people, but if I sample this way, I get a pretty good idea of what people in the entire city think without isolating a particular subgroup or leaving out a neighborhood or things like that. So we're going to go with C here because it seemed to be significantly better than the other 3. So these are kind of some questions you might see when it comes to sampling. You might not like this as far as a math question goes because it seems a little vague and up to interpretation, and it is. But hopefully you can kind of work. You want to look for words like this. You want to think about what's best, what's going to give you the best sample. You want a random sample. And like I said, this example was fun because we got to rule out some things and talk about why. So another thing in this section is what's called frequency distributions. In a nutshell, a frequency distribution takes a data set, and there's one here, and kind of breaks it up into how many of these data points fall in a particular group. So I've already made a frequency distribution for this data. Let me read it, show you the distribution, and kind of tell you what this term means again. So as of 2011, the following are the ages in chronological order at which the U.S. presidents were inaugurated. So their age on Inauguration Day. So here we have 44 presidents and their ages on Inauguration Day. And what I've done is I have constructed what's called a group frequency distribution. where I made classes starting with 41 to 45, and I made classes with the same width. So let me show you what I did and then kind of talk about some of these things. So it said start with classes of 41 to 45. So I made a group. I said everything in this group is going to be ages from 41 to 45. So once I made this, I went into the data and I counted the number of data points that fell into this category. So for example, there's a 43 here that fell into this category. And where's the other one? There's a 42 here that fell into this category. They were the only two, and since there was two, I wrote the frequency is 2. And then it said make other classes that are the same width. So I went on and made classes that are the same width. This was 5 ages, this is 5 ages, and I kept going until I ran out of ages. So for the next one, I counted the 46 to 50. Any number that was in here got counted. There were 9 of them, and so on. So a group frequency distribution involves taking your data, making some sort of age ranges that are all equal widths, and counting up the frequencies. A regular frequency distribution, sometimes you don't see this grouped. Group means that we have an age range. Sometimes you see like a regular frequency distribution where you see just a particular number here, like how many 5s were there, how many 6s were there, how many 7s or 8s or 9s, and you would count up the exact number of things. I'm just making something up here. What makes this a grouped frequency distribution is these are just numbers, a single number. So these are ranges of numbers. So anything in this range gets counted, whereas this would be how many 5s are there, how many 6s are there. So anyway, take a look at this. That's what this means. The other big thing when it comes to making frequency distributions is you need your classes. We'll call these classes. These are classes. They all need to be the same width. So in this case, the width was 5. There's 5 numbers here. So they need to be the same width in order to be a good frequency distribution. And but yeah, otherwise you're just counting data and putting them into the categories. So let me show you why frequency distributions are helpful. For one, we can kind of see which age group was the most frequent. This was interesting to me, that there were 15, 51 to 55-year-olds who were inaugurated as president, and it's significantly more than any other age group. But also we can make things called histograms and frequency polygons from frequency distribution. So I just cut and paste that frequency distribution. It's right here. And I'm going to show you how to make both a histogram and a frequency polygon. And for the sake of time, I'm going to put them on the same graph. Okay. So histogram is a bar graph that measures frequencies. And I know you've seen bar graphs before. So this is really a bar graph that measures frequencies instead of typically other bar graphs, you just see categories. How many are in this category? So I'm going to make a histogram first, and in order to do this, I need to mark off my bars so I don't get too confused. So I want one bar to include 41 to 45, the next bar to include 46 to 50. And the way I'm going to do this is I'm going to separate the bars with the number that's halfway between these endpoints. So this right endpoint is 45, this left endpoint is 46. So I'm going to put a bar here at 45.5. And that's going to separate those two bars. Then I'm going to put a bar here between these two. That's going to be halfway between these numbers. It's going to be 50.5, and then so on. So I'm going to put a bar here, and you'll see what I mean when I start drawing this. I'm going to do 55.5, and then I'll put one between 60 and 61. This would be 60.5. And then I need to extend this out a little bit more. And then I'll put a bar between 65 and 66. This will be 65.5. And then I want to measure the frequencies. So my frequencies go up to 15. So let's do 15, 10. That's not going to work. Let's put 10 here. Let's put 5 here. I'm just plotting this now. My ages are going on the x-axis, my frequencies are going on the y-axis, and now I'm going to just draw bars. And once I draw this, hopefully you can kind of see what I've been getting at. I'm just trying to do it, and then I'll talk you through it. So my 41 to 45 range, I have 2 things. So this is going to be 2 units high. My 46 to 50, I have 9 presidents. So this is going to go up to 9. My 51 to 55, I have 15, so this bar goes up all the way to 15. My 56 to 60, I have 9 again. And then my 61 to 65, I have 7. So it's right around here. So I need to make one more tick mark. And then, so this will be like 70.5 or something. This will be 2 units high as well. And then you have some kind of distribution. So this is essentially what a histogram is it's a bar graph that measures the frequencies of the data. So on the y-axis, you should read these as frequencies. So this tall one at 15 means there's 15 things between 50 and, or 51 and 55. I should put something here. Let's put 40.5 here. This little tick mark. So there's the histogram. And the frequency polygon, what it does is it is a, you make it sort of from, I think you can make it from your bar graph. And what it does is it's a shape that pretty much outlines the histogram itself. So what you do is in the middle of these bars at 2, I'm going to put a little dot here. That's going to represent the frequency of this group. And between these 2 bars, I'm going to put another dot. That's going to represent the frequency of the 46 to 50 group. Between these 2 at 15, I'm going to put a dot. That's going to represent the 51 to 55 group, and so on. If I take the middle of these ranges and I put a point at the top, or at whatever the frequency is, so this is 9, this is at 15, this is at 9, this is at 7, this is at 2, then I can make a frequency polygon by simply connecting these dots. And these should be connected with straight lines. I'm trying to make straight lines. Maybe that goes down to there. Sorry, my drawing isn't very good. But so what these things do is they allow you to kind of see the shape of the data. In other words, if you're looking at a distribution, if you've ever kind of heard of a bell curve, we imagine a bell curve having a high middle and being symmetric on either side. This histogram kind of looks like a bell curve to me in that the middle is really high and it's not quite symmetric, but it could be, and it kind of leans a little more this way than that way. The frequency polygon gives you another shape where you can kind of see the highest parts in the middle, and then it kind of trails off to the right. It's a little steeper on the left, but it allows you to take a lot of data. We had 44 data points and represent them in a certain way so that it doesn't look like just 44 numbers. Okay, so in other words, you can see more about my data from this picture than you can from this. This is kind of a pain to look at. Whereas this, on the other hand, kind of gives you an idea of the shape, the distribution of the data. How is it distributed? Is there more here? Is there more here? So that's the general idea. So there's the frequency polygon in red. The histogram is in blue. And this is the frequency distribution we made on the last example. Okay, the last example I wanted to show you is another way of taking a lot of data and representing it in a way in which you can maybe see more about it. This is called a stem plot or a stem and leaf plot. These terms mean the exact same thing. One of them might be a little more technical than the other. I'll let you guess which one. But here's statistics test scores for 40 students. So there's 40 data points here. And the way a stem plot works is you take your data point. So for example, I have the point 47 here. And you take any data point that's in the 40s. You put a 4 here to represent the 40s, so something, 4 something, and then you plot the leaves. So there's 47. See 47, the tens digit is there and the ones digit is here. 45 is right there. You can see it. The 4 is the tens digit. The 5 is in the leaves. And then there should be a 43 on here. This says 43 is in our data set somewhere. Kind of feels like where's Waldo? Oh, it's right here. 43. So 4 is here, 3 is here. And so you do that for all your data points. So everything in the 50s gets plotted here. 57, 54, 56, you can see they're all on here. And then once you're done, you have another sort of representation of your data. So there's 40 numbers here. And you can, if you turn your head to the right, you can kind of see a distribution. In other words, if you turn your head to the right, you can kind of see this is the high middle, and it's almost bell-shaped, except it leans a little bit more this way now than that way. But you can see a lot of the data better than if you were just to look at these 40 numbers and try to learn something about it. So histograms, frequency polygons, stem plots, and there's a few others that we're not going to look at. are ways of taking a lot of data and turning it into some sort of shape or representation so that you have some kind of idea what the data is as a group. So if I were to have 200 things, I could still make a stem plot and it would still kind of look like this, which is kind of interesting. So same with the histogram. If I had 200 data points, I could still put it in a histogram. It might still look like this. The frequencies would be a lot higher, but it should look the same. So that's your little introduction to statistics, sampling and data. And in the next few lectures, we're going to look at some specifics, things that we would use to learn about, use a sample to learn about the population.